Hi everybody, it's Mr. Zarzak here, and in this screencast I'll be working questions 1 and 2 of Student Practice File 2-3. So if you haven't already, please go on to Schoology into the Practice File folder for the Unit 2 and grab a copy of this and load it up into Notability. Looking at question 1, okay, it says above left, use the scale 1 centimeter is equal to 5 meters. So you've got these baseball players on top of this cliff, and then you've got this metric ruler here. These are in centimeters. Okay, and so there's an equivalence here that we're going to use for the calculations that we do in meters, translated into centimeters using that ruler. Anyway, so going back to question 1, above left, use the scale 1 centimeter is equal to 5 meters, and draw the positions of the drop ball at 1 second intervals, neglect air drag, and assume gravity is equal to 10 meters per second squared. Estimate the number of seconds the ball is in the air. Okay, and so what this really is we have a picture of a baseball player over here on the right who's going to throw the ball, but before we worry about what's going on there, what we're really going to be doing here is we're going to be reviewing Freefall. Okay, so over here I'm just going to mark this down that this is Freefall. And you should do the same, okay? So take these notes, treat this like guided notes. All right, and when we deal with Freefall, all right, the position, okay, the displacement from rest is just equal to 1/2 AT squared. Now, we've been working with this idea of vectors. Okay, and so because the distance that the ball falls here is just straight down, I'm just going to add in a little subscript of y. So that says dy equals 1/2 AT squared, and that acceleration is just due to gravity, which is also in that y dimension, okay, because it's in that downward direction. So I'm going to add a little y there too. Okay, so that's just to make my equation more specific. I'm talking about a displacement down, so I use 1/2 times the acceleration down, which is gravity times time squared. Okay, so in order to do this, okay, I'm actually going to sneak my work in down over here next to the cliff, and you'll see why here in just a second. Okay, so I've got my equation written already, so I'm just going to start subbing in. So at 1 second, so I'm going to call that D1, that's 1/2 times 10 meters per second squared times my time of 1 second squared. Okay, so some quick math, half of 10 is 5, and 1 squared is 1, and 5 times 1 is just 5, so that first position, D1, is at 5 meters. Okay, so I'm just going to go ahead and repeat the process for 2 seconds. So I'll call that D2. So that's just 1/2 times 10 meters per second squared times 2 seconds squared. Half of 10 is 5, 2 squared is 4, 5 times 4 is 20. So at my second position, all right, the ball is 20 meters below where it's been dropped. Now, before I go on any farther, okay, I've got this scale of 1 centimeter is equivalent to 5 meters. So let's figure out where I am here. With 1 centimeter is equal to 5 meters, well then, after 1 second of falling, I'm just 5 meters farther down. So for this first position, that's pretty straightforward. Okay, 5 meters is 1 centimeter. Okay, so I'm just going to go, I'm just going to draw a little line here from 1 on my ruler here to where it hits this dash line right there. Okay, and where I see that, I'm just going to put a little red spot, okay, to represent where the ball would be at this point. So just like that, okay. Now, for D2, I'm 20 meters down. Okay, so for that, I'm actually going to convert using factor unit label, and I'll do that down here where I've got some space. So this is for D2. All right, D2 is 20 meters. So turn that into a fraction. Okay, and my scale is 1 centimeter is 5 meters here in the directions. So for every 5 meters, that's equivalent to 1 centimeter. Okay, and so if I do this, you'll see that the meter part factors out because it's in the numerator and the denominator. And really what I'm doing mathematically is 20 times 1 divided by 5. So that second position, D2, 20 divided by 5 is 4 centimeters. Okay, so I'm 4 centimeters down. I'm going to use that trick, okay, for each of these. So I go find 4 centimeters on my metric ruler. Okay, and I'm just switching to a thin black pen just so I can kind of mark the position. So I'm just going to draw a straight line from 4 centimeters over to here. Okay, and then where it hits that dash line, I'm just going to put a red mark to show the position of where the ball would be at this point in time. Notice that the ball was dropped from rest up here at 0, so I'm just going to put a little red mark over that original baseball too. Okay, so I'm not down to the bottom of the cliff yet, which means I have to keep calculating. Okay, so back to where I'm doing my work over here, so this would be D3. So 1/2 times 10 meters per second squared times 3 seconds squared. Half of 10 is 5, 3 squared is 9, 9 times 5 is 45, so D3 will be at 45 meters. And again, because my scale is 1 to 5, okay, just like I did down here with the 20, I just really divided the 5 into the 20. So I'm going to divide 5 into 45, which is 9 times. Okay, so that's equivalent to 9 centimeters. All right, so I'm going to find my 9 centimeter line, which is down here. And once again, I'm going to draw that line straight from 9 centimeters, okay, over to where it hits the dash line. That was off a little bit, so I'll just move it, no big deal. Okay, and then change that red pen, and then I'm just going to mark that off, okay, where it hits the dash line. Okay, and so a picture is emerging of this accelerated motion. Okay, so next calculation, because I'm still not at the ground, so this would be D4. Okay, so D4, 1/2 AT squared, so that's 1/2 times the acceleration of gravity, which is 10 meters per second squared, times 4 seconds squared. So one more time, half of 10 is 5, 4 squared is 16, 16 times 5, that's 80 meters. So D4 equals 80 meters. Okay, and if I was going to convert that from meters to centimeters, once again, my scale is 1 centimeter is equal to 5 meters, so I'm dividing 5 into 80, which just so happens to be 16. Okay, so I'm going to switch over to black pen. And one more line down here at the 16 centimeter line, or mark, excuse me. Okay, so straight across. Okay, and look at that, I'm right at the bottom of the dash line. So I'm going to go ahead and mark this off. So I'm right at that point where I'm just above the ground there. Okay, and now I'm ready to answer question 1, which is estimate the number of seconds that the ball is in the air. That's the last part of the question. Okay, so right at this 4 seconds, I'm right below the ground. So for an estimate, that sounds pretty good. Okay, so that's my estimate, 4 seconds. We'll make that a little thinner. There we go. Okay, so not just question 1, but this is really about projectile motion. Okay, so how do we get projectile motion? Well, that's where we need to read number 2. Okay, so number 2 reads, above right, the 4 positions of the thrown ball with no gravity are 1 second intervals. At 1 centimeter is equal to 5 meters. Carefully draw the positions of the ball with gravity. All right, so before we go any farther with reading this, let me explain what this means in the diagram. Okay, so it says, essentially we're using our imagination here and saying if this baseball player threw this ball off the top of this cliff, but if there were no gravity, well then the ball wouldn't move down. It would instead move in a straight line at a constant speed. Okay, and so what's really happening up here, okay, is this just an idealized picture of constant velocity. So I'm just going to add that label up here. So we've got this constant velocity, which is just the same speed and direction. All right, and we've seen this before. For constant velocity, how far we go, d, is just equal to the product of our velocity times time. That's just speed times time is equal to distance, but we're talking about vectors here. So we're talking about displacements and velocities as opposed to speeds and distances. Okay, and this is horizontal, so we call this dx, and this is vx. That's what these positions of the ball here are right now. Okay, so I'll just kind of follow what I did before, and I'm just going to kind of trace these over with little green dots. Okay, and a picture emerges. See, the space from one dot to the next remains constant if we're moving at a constant velocity. And that just means that you're going to cover the same distance for every unit of time. So how far you go between time 1 second and time 2 seconds is the same as the distances you go between time 2 seconds and 3 seconds. Now that's not the same as what we get with free fall. If we look at the dots at free fall, the spaces between the dots gets progressively bigger because as the ball falls, it's speeding up, it's accelerating. In fact, what we're really looking at here with the baseball player dropping the ball is a picture of accelerated motion. Oops. So I'm going to write that in here in red. Okay, that's what free fall is. It's accelerated motion. Okay, and the point of all of this is that this idea of projectile motion is really a combination. It's a compound motion. So if I go back to the question here, okay, so I was reading it along. Above right, the 4 positions of the thrown ball with no gravity are at 1 second intervals at 1 centimeter is equal to 5 meters. Carefully draw the positions of the ball with gravity. Neglect air drag, assume gravity equals 10 meters per second squared. The idea here is that you connect the positions with a smooth curve to show the path of the ball. Okay, what does that really mean? All right, well, we're going to just play this game of connect the dots. All right, so if I go back over, all right, each of the 2 balls is released from the same position. So you can see that the first red dot up here and the first green dot are at the same position. So let me make that black pen just to stay consistent. Okay, so these here are together. Okay, but 1 second later, all right, the ball has fallen down this 5 meters. In fact, I think I'm going to label those as I go too. So this was 5 meters over here at 1 centimeter. Okay, and just for recap, at 2 seconds that was 20 meters. And at 3 seconds, what was 3 seconds? 3 seconds was 45 meters. And then at 4 seconds, that was that 80 meters. Okay. All right, so when the ball was 5 meters below where it was dropped, okay, if it was thrown and there was no gravity, it would be at this second position of the green dot. So what I'm going to do is I'm going to draw a line, a straight line, going from the position of this 1 second red dot. Okay, I'm going to take it all the way over here to just below where I see the green dot, and then I'll draw a vertical line down. Okay, so those intersect, or at least pretty close. Okay, and what that's going to do is it's going to give me a map of what the projectile motion looks like. So at 2 seconds I was 20 meters down, so if I take this next red dot here, I'm going to drag this over until it's about underneath where the green dot is. Okay, I'm going to do the exact same thing with the green dot. I'm just going to take and drag a line down like this. Okay, and if they don't quite intersect, that's all right, because I'm going to put a little dot there that'll kind of make them intersect. Okay, and I'm going to do the exact same thing for this 45 meters. Okay, and in fact, this work is just barely in my way here, so we're going to shrink that down a little bit to get it out of the way. All right, so I'm going to pull this over here till it's definitely below where the green is. Okay, and clean this up. Okay, and then I'm going to draw another vertical line down with me so that those intersect, and then one more all the way over here when the ball is 80 meters below where it was dropped, right at the instant, right before it hits the ground here. All right, and then connect with this last green dot up here. Okay, so these intersections, they're points. Okay, they're points along the motion, and that motion is what we call projectile motion. All right, so that at these locations, these intersections, I'm going to take and just mark those off with the blue dot like this. Or excuse me, let's do black. Yeah, like that. And here, and here, and here. Okay, the initial position too up here, where the baseball player first threw it. Okay, and so if I take and I connect these, so I'm going to go to my highlighter, I'll select blue. Okay, if I take and I connect these together, all right, the shape that I get, it's not a straight line but a curve. Okay, that curve right there is half of a very important shape in physics, and that shape is a parabola. See, this projectile motion is parabolic motion. So I'm going to add that too. See, so projectile motion, too big. There we go. Projectile motion is the same as parabolic motion. Oops, I can't spell. There we go. All right. And last but not least, okay, it says, how is the motion in the vertical direction affected by the motion in the horizontal direction? Well, projectile motion is what happens when you combine constant velocity in one dimension with accelerated motion in the other dimension. When you put together free fall and constant speed, that's how you get that parabola. And the reason that it works is that because these two motions are independent of one another, or in other words, horizontal and vertical motions are independent. It's for this reason that the ball thrown sideways off the cliff and the ball dropped from rest off the cliff would both be in the air for 4 seconds. They would hit the ground at the same time. This has been Mr. Zarzak. Thank you for watching, and I'll see you in class.